and I have to do this, even though it's supposed to pick up everything, but it does not. And I can amplify my voice now. Do it. You're trying to get used to it. Okay, so if you're wondering about for this module, so far there's no like assignments, those sort of things. So I have actually already uploaded in Moodle, right? I know not everyone has gone up to Moodle yet, but I could see that some of you went to Moodle already. So Moodle would have the assignments which you need to submit 1 week later.
Huh?
So I can hear that, yes. So I'll show you why is it that suddenly there's a 1 week later thing. So if you remember in our introduction, I was talking about this. Formatted assignment submission. That is on the 23rd October at 5 p.m. Submitted via Moodle. So if you don't know what is Moodle, it is an online platform. So I have already sent an email to the administrator at IFA. IFA sends you this website link. Click on that, and then the password for it is SIP 3050. That's the course code for this module, Dynmaics Lt4. So go over there and then retrieve your assignment, which is a 1 question. And then that 1 question, do it on a foolscap paper. You can either, after you complete it, scan it, or take a picture under good
I
lighting.
need to keep my face.
And then submit it
Never mind.
online, where online, in Moodle. So look through Moodle. There will be places that allows you to do the submission. That is only a 1 question assignment, 1 question only. Submission is compulsory. There's no mark on this submission. Right? It's a formative assessment. Formative means you must do no mark. Must do but no mark. I also, over the weekend, communicated with your module, the module counterpart, to talk a little bit about exam. So, exam is going to be 4 questions, so don't listen to your seniors. They passed already. Yeah, okay. Right. You have not. So who can you depend on? Not on them, because they passed already. Right. I am responsible to you. Right. So I'll give you all the good stuff. What are the good stuff? Exam will be 4 long questions. 4 long questions is a 2-hour thing compared to your seniors, which is a 3 hours thing. Alright, 6 questions that they have. Choose 5. Section A, Section B, but you don't have that anymore. So you should be listening to what I say, not what I say. Right? 4 long questions. As I told you before, there are 2 lecturers in Glasgow. So one of them is Dr. Patrick, Dr. Ian. And they'll be sending 2 questions each. That's why 4 questions. So each question would be 20 marks. And you only need to do 3 out of 4 questions. So 3 questions that you do, 20 marks each, that will get you to how many marks? 60 marks. After you got 60 marks, we'll normalize it to 100 points. right, 100 marks. So I'll multiply by a factor of 1.333. So what that means is that for every mark that you lose in this question paper, it will cost you 1.33 marks. So don't trivialize that one little mark in this kind of paper, that the denominator is only 60 marks. The denominator is not 100. After you got the 60 marks, then I multiply by the factor to make it 100 marks. Okay. So the Dynmaics data sheet that you have, that's the one that we'll be using. Alright, so it's also available in your Moodle. So that's all the information that I managed to gather from last go. In fact, if I did ask, they didn't tell. They also didn't prepare your answer like us. So I think that's sadly that gears into motion over that side. So this is what it is. This information, you don't have to write down, take picture, because it's also available in Moodle already. So Moodle is my only source, only platform to reach out to you. So make sure you get hold of that web link and then do your enrollment key, which is the password, and then you'll be able to access all the information that I posted up there. For those of you who are weak in partial fractions, moment of inertia, all these fundamentals, I've also included some worksheets in there. So it allows you to do the practice. So please do all those things. And since the assignment is only one question, maybe some of you will feel that it's so easy, very completed that within 1 hour. You get more. Yes. I've inserted right at the end of your Moodle page this thing that's called practice questions. So practice questions, there'll be a lot more questions in there, from the easier ones and then to some partial data questions. Right. So it allows you to do the practice of that. Practice question need not be submitted. Only your assignment question, one question that you need to see. Right, so the submission deadline for that will be on 24th, right? I think this should be skipped in line. The submission deadline 24th is also written in Moodle. So you could see that, submission deadline is on 23rd, and on the 24th, we'll have a tutorial. Right, the tutorial will discuss about that assignment. All good? Yeah. Very good. Okay, let's continue where we left off 2 weeks ago. So, I hope you haven't forgotten what we covered last week. We were over here working on this question. There's work example 2.4. And we kind of solved part 1, and then now we're going into part 2. So part 2, if you don't know where to get the question for this, I've also inserted in Moodle. So it's going to look something like that. Right, this question over here.
Last week there's no dynamics.
Start of the question. So it didn't really say part 1 and part 2. So 2 paragraphs, so I just label it as part 1, part 2. So the second part, it gives you all these variables. So what I'm going to do is to write down all of them. You're given a few of these parameters, like mass, the length of that rod or that beam is 1 meter. A, which is the distance to the point where you have your damper, that's 0.5 meters. The spring constant that's connected to that point as well, that's 640. Newtons meter. And then your damping coefficient, that's 32 Newton seconds per meter. So the question wanted you to find out what is that theta T response, or sometimes called time response. The time response, where you kind of pull that spring to displace by theta naught. So that theta naught over there, this one is your initial displacement. So you displace that spring and then you let it go and let it oscillate. So we have already solved what is the form for that second order differential equation. It's right at the top, so I'll scroll quickly through that. Right? I'm going to copy this one down, that equation. So theta dot dot plus C over M A over L squared, theta dot A over M A over L squared, theta equal to 0. So since we're given all these variables over there, so now we can just substitute in the C and the M. That's 32 over 1. A over L, that's 0.5 over 1 squared, theta dot, plus K over M, that's 640 over 1. And then A over L again, squared, theta equal to 0. So if I work out all this, what I'll get is theta dot dot plus 8 theta dot plus 160 here equal to 0. So if you're up to solve what is that theta t, which is the time response, out of this second order differential equation. So if you're up to solve that, then we need a few things. There are actually a few methods that you can use to solve that. So before I solve that, I kind of want to work out some other parameters in order to get some understanding of this second order differential equation. What sort of thing? I want to find out what is omega n, what will be zeta. So omega n, we actually had that equation right up there, right? Omega n. We have zeta expression. We have omega d expression. So I'm going to use all of that. So omega n expression, if I were to use that expression, I'll just substitute the numbers straight on. 0.5 over 1, and I work it out. There's 12.65 radians per second. That's kind of how I write 1 with this little tip at the top. Okay, it's not 9, it's 1. So zeta, from the expression at the top, I'll just substitute the numbers in there as well. So please refer to the top part. So that's 32 multiplied by 0.5. 2 times 1, and then square root 640 multiplied by 1. So if I work this out, that is 0.316. Is there a unit for zeta? There's no unit for zeta. If you put a unit for zeta, what will happen? Minus 1 mark. And that 1 mark costs you how many marks? That's so expensive. So over the years, I also discovered some students would, out of fear, write down here, no units. Or you don't have to do that. Just leave it alone. Leave it alone. But what I want to mention is that zeta equal to 0.316. What does that tell us? What is a zeta? If zeta is less than 1, what does it mean? It's an underdamped system. If zeta is equal to 1, it's a critically damped system. If zeta is greater than 1, then it's an overdamped system. So just by working this out, to try to find out what is zeta value, I have that conclusion that this system is actually an underdamped system. And I'm going to use this red marker put an asterisk over here because later on I'm going to refer to it again. So later on I'm going to refer to this part where zeta is equal to that value and is an underdamped, it indicates that it's an underdamped system. So omega d, which is omega n square root 1 minus zeta squared, this formula is available in your data sheet. I'll substitute omega n 12.65 and then that zeta squared 0.316 squared. Work it out 12 radians per second. So we can use the omega d expression that we had at the top because if you look at the top here, omega d, right? This is omega d expression. You can also use this. You end up with 12 radians per second as well. Both are the same. So now that we have that, later on, I'll make use of these values. In order to solve this second order differential equation, I'm going to introduce to you three methods. In the exam, you can use any of these three methods. Some methods will be easier for you, some methods will be more difficult for you, so you can choose. But I'll list down these three. And as we go along in further lectures, I may just selectively use either one. I wouldn't all the time give you all methods that are possible. But for this one, it's the first time, so I'll write down all the methods that are possible. The first method. Method number one is the Euler's method. So Euler's method, in order for us to start using it, I want to have some understanding of these initial conditions. So the initial conditions here means that when theta is at time 0, that's how I read this mathematical expression. When theta is at time equal to 0, I have this equal to 0. That means I kind of stretch that spring to displace that feet by a certain angle, and that certain angle is theta naught. And then I release it, and then the whole thing will oscillate in that way. Okay. Why would it oscillate in that way? That's because it's an underdamped system. If it's an overdamped system, after I displace it by theta naught, and then release it, if it's an overdamped, then it's going to come back. That way. Overdamped. If it's a critically damped system, after I displace it by theta naught downward, and I release it, then it's going to come back that way. No bouncing at all, as described by the expression. What expression was that? This expression that you saw in your data sheet over here. So for an underdamped system, you can see that it has a cosine and sine component. That means it will oscillate. That oscillate will decay. How do I know? Because there's an exponential to the power of minus sign over there. E to the power of minus sign is a decaying term. It will slowly decay. So that's why I know that for an underdamped system, it will oscillate. Does that mean there's no oscillation expression for the rest of it? It's actually true. Yeah? If you look at critically damped system, there's no sine or cosine component. That means it will never oscillate. It will decay because there's an exponential form. How about for overdamped system? Again, you can see there's no sine or cosine component. Right? But there's an exponential decay. So that's how we know, just by this value of zeta, that's your damping ratio. If it's less than 1, equal to 1, more than 1, we already know what kind of general equation, expression we're going to get. So later on, we also try to make use of this knowledge. So the other part about the initial condition is where we have theta dot at time equal to 0. Theta dot over here refers to velocity. Right? Theta dot, that's velocity. And we know that that velocity at time equal to 0, that's when I pull the beam down that way. That velocity at time equal to 0 is equal to 0. So these are the two boundary conditions, or two initial conditions. So what we do next for an Euler method is to let theta, which has a general form. Maybe I'll move this a little. Let the general form of theta be equal to this expression. This expression. And I'm going to show you that data sheet again so that you can compare them side by side. We know that it's an underdamped system, and the underdamped system has this following form. What differs between what I wrote down for this is that I changed the x into theta because this system is a rotary system. So that x will become theta. This x naught will become I theta naught. This e to the power minus zeta omega nt, that one would stay. And then over here, you can see that this term is cosine omega d, cosine omega d, and then this whole chunk of it, and then sine omega dt. Right? So in my general form that you can see over there, this general form over here, it has sort of like that format. Right? I have over here my a sine omega dt. Over here, I don't know what expression I'm going to get yet, so I put all these things in my general form as a, and then sine omega dt. The general form for this, it will be b cosine omega dt. So that's the general form. And why is this important to me? Because now my task is to find out what is this coefficient a and b. In order to find out what is my theta t expression, right? This theta t expression. That was what the question was asking just now over here. What is your theta t expression? It has its general form, I know. Why not the other form? That's because I know that it's an underdamped system, so it has to follow that format. Why not I use exactly what is in that set of data sheet, where I have this part here is zeta over square root 1 minus zeta square. Why don't I just copy everything in? Well, that's because we have this case here with this kind of initial conditions. Different initial conditions will result in different kind of coefficients. So this is one general form. And later on, we'll put in our initial conditions to solve A and B. A and B are two unknowns. For two unknowns, you need two initial conditions. And we do have two initial conditions over here. So that's what we'll be doing. So you can see that we need theta at time equal to 0. So when theta at time equal to 0, this term over here, that means t over here will become 0. Maybe I'll just write down. Theta at time equal to 0. This t here will be equal to 0. And then you have a sine omega d, and this t again equal to 0, plus b cosine omega d, and this t at time t equal to 0. So e to the power minus 0, what do you get? Generally, e to the power 0 must, anything equal to the power 0 must be equal to 1. So this will be 1, and I'm going to write an arrow over here to say that this whole thing that I just strike with an arrow, this one is 1. How about sine 0? Sine 0 is 0, so my a here will be out as well. This whole thing will be 0. Cosine 0, that's 1. So if I put everything together, theta at time equal to 0, that is theta naught. Right? Why do I know that? That's because that's my initial condition. And then this is 1, and then I have b, and then that's 1. So theta naught and theta naught can cancel off, and then my b is equal to 1. Some students, after cancelling, wrote b equal to 0. I don't know how does that happen. Yeah? Cancel doesn't mean they are gone forever. It's just dividing throughout by theta naught. So if you divide two sides by theta naught, you get that equal to 1. So the other initial conditions that I want to make use of is this: theta dot at time equal to 0 is equal to 0. So what I can do is to differentiate this term over here. So if I differentiate that term, I get that, this one. Differentiate this term over here because this exponential form is multiplied to this square bracket. So there are two t's that I can see in there. One t resides in the square bracket and the other t resides in this exponential form. Theta naught is actually a constant, so that constant would stay. So what I'll do is to differentiate that. So I'll start with holding this constant. You know the differentiation product rule. Product rule. So if you differentiate a times b, then you differentiate a and hold b constant, plus differentiate b and hold a constant. Yeah, that's your product rule. If you look at me like wild eyes, yeah, I was sure that I was talking the right thing. It's just that you didn't know it yet, or you've forgotten. Waste time. So I'll hold this constant first, right? So e to the power minus zeta omega n t. But don't worry about that. Yeah, I have some practice questions in Moodle, so please make sure that you go over there and practice what you should actually know, right? And don't put it off like I'll do it during my Deepavali next week thing, and you'll just snowball it, seriously. Okay, so I'll differentiate this now. So differentiating a sine omega dt, I'll get a cosine omega dt, and then differentiate the inside with respect to t, so I get omega d over there. Okay. Plus, if I have to differentiate this, then my b would be there. Differentiating cosine omega dt is sine omega dt, and then differentiating the inside. So differentiating cosine, you get minus sine. So that was what we did. Hold this constant, differentiate this. The next one, plus theta naught, differentiating this. E to the power minus zeta omega n t, and then bring that factor down. So you have this part here that's minus zeta omega n, right? That's how you differentiate e to the power of this. So after you differentiate that, the rest of it, you just write it down, holding that as constant. So I'll write it down. It's d cosine omega dt. So that's your differentiated form. And in order to apply the second initial condition, that's theta dot naught, I'll have this term over here, e to the power minus zeta omega n 0, and then this term over here, right? If this is equal to 0, that means you have omega d, a omega d. Minus the sign 0, it will become 0. Minus omega, minus zeta omega n theta naught. And then this term would become 1. Right? And then actually this one is also equal to 1. And then the sine term will become 0 if you substitute 0 to t. And then this term here will become b and then 1. So in this case, theta dot at time equal to 0 is equal to 0. That's our initial condition over here. And I'm going to pick up everything together. So this would become theta naught a omega d. And then that one will become minus theta omega n theta naught. And then there's b over there. Cosine. So b was actually 1 that we calculated right over here, b. Okay, we already found that. So that one would be inside here. So theta naught is a common factor, so I can cancel it out. Right, divide throughout by theta naught. And then we left with the term a, so I express a as a subject. So what I'll get, right, 0 first. 0, a, and this omega d will become omega n square root 1 minus zeta squared, and minus zeta omega n. So again, divide throughout by omega n. So if I were to do that, this will cancel off. So a will become zeta over square root 1 minus zeta squared. So now we have the coefficients. A is this, and b is equal to 1. So now we can substitute the coefficients a and b into that general form. So I have theta t equal to theta naught e to the power minus zeta omega n t, and the a would be zeta over square root 1 minus zeta squared sine omega dt, plus the b will be equal to 1, so this will be cosine omega dt. So we have seen just now what are the zeta and your omega n values. So zeta, as we solved just now, it was 0.316. Omega n, we solved just now, it was 12.65. So if you put them together, then your theta t will become minus, if you do the calculation, you should get 4 t. Right? Zeta multiplied by omega n. And this term over here, if you work it out by substituting all your 0.316 into it, so you substitute that, then you get 0.333. And sine omega d, we have solved, that was 12. So I think it's good to write down units. Yep. So I can fill in this is 12t plus cosine 12t. This is your answer. This is first method. The second method. The second method is to use Laplace transformation. Personally, I like Laplace transformation. Why? because then I do not need to have to know what is the general form. This is the advantage of that. You do not need to know what is the general form. If you have this general form wrong, then after your differentiation and substitution, your final result will also be wrong. Right? So let's have a look at the Laplace transformation. Again, we have our initial conditions. So you can use any of this method during your exam. So theta at time equal to 0 is equal to 0, sorry, is equal to theta naught. And theta dot at time equal to 0 is equal to 0. So Laplace transformation requires us to take the Laplace transformation of the expression theta dot dot plus 8 theta dot plus 160 theta equal to 0. We need to take the Laplace transformation of that. And I'm going to use this L looking thing to represent taking Laplace. So if I were to do that, Laplace transformation of theta dot dot, I get s squared theta s minus s theta naught minus theta dot 0. And Laplace transformation of 8 theta dot, that will be 8 s theta s minus 8 theta naught. And then plus 160, taking Laplace of theta, that means I have theta s and equal to 0. Now from our initial conditions, this one will be equal to 0. That was coming from here, right? And I have some common factors. So I have this theta s, theta s, theta s. So I'll take all of them together. Theta s. So in there, I'll have s squared plus 8s plus 160. And then bring the rest of them to my right hand side. So the rest of them will be this and this, of which you could see that there's a common factor, theta naught. So if I bring it to the right hand side, it becomes s plus 8 theta naught. So now I can express theta s as my subject. So theta naught, I'm going to bring it to the front, and then the rest of it, s plus 8 divided by this whole thing, s squared plus 8s plus 160. So because zeta was less than 1, that means it's an underdamped system. If it's an underdamped system, then I need to factorize this denominator in certain way. In what way? So I write down that denominator. That denominator, s squared plus 8s plus 160. I need to factorize this in a special way. I need to break it down into this form. S plus certain thing squared and plus certain thing squared. How do I factorize it? So I'll only say this once, right? This is the technique to factorize. If you need to factorize this, look at this middle term. Right, so here will be s squared. Look at this middle coefficient. It's 8. Take 8 divide by 2. So no matter what number is that, take that, divide by 2. So you get 4. Right? So s plus 4, whole thing bracket squared. So the last coefficient over there, you will have it as 4 squared. So 4 squared is 16. Right? 4 squared is 16. What you need to do next is to find out from this 160, minus your 16. What do you get? 144. Square root of 144? 12. So this term here is, that's how you factorize it. It's a technique. If not, there's a set of equations behind it. So this is another technique. Later on, I'll solve some other questions and we'll revise. So now that I've factorized it, I'll put it back. S plus 8, S plus 4 squared plus 12 squared. And then there is my theta naught. Maybe I'll write theta naught in the front. Because I find that over the years, some students forgot that there's that theta naught. Right here is theta naught. So what I need to do next is to further factorize this. I want to split this up into the following way. With that denominator, this denominator. I have this numerator, it's going to be s plus 4. And if you're wondering, why do I put that numerator as s plus 4? There's actually a good reason for that.
What?
So if you look at your Laplace matrix, now I can't do an inverse Laplace on this. I cannot, because inverse Laplace means you go that way. And you can see that there's no expressions over here, not even this, correspond to this point. Yep. There's no expression over there that corresponds to that point. There's one that's very near, the last one. It requires this to be 4. That's why I put a 4 here. So if I put a 4 over there, that means I will need 4. I will need 4 at this numerator. So when you combine this plus, and you get s plus 8. Yep. And this 4 over here, 4 over this. You think you can do an inverse Laplace? Actually, what you need is 12. Right? You need it to be 12. Yeah. So what we do is that if I need this to be 12, that means I need to divide that 12 by 3 in order to get 4. Right, 12 divided by 3, I get 4. So now you can start to do inverse Laplace. Inverse Laplace is written as that L to the power minus 1. You just need to write that, I will understand what you mean. Inverse Laplace of theta s is theta t. Theta naught would stay. This inverse Laplace will get me e to the power minus 4t cosine 12t plus 1/3. So multiply over here. And then inverse Laplace of this, I will get e to the power minus 4t sine 12t. So I can bring out the common factor, which is e to the power minus 4t. cosine LT plus 1/3 sine of t. Exactly the same as just now. So if you look back just now, that term was 4. I kind of like, because you have none, so you can write either one first. This 1/3 is 0.333. So the other thing, you can use either method. Okay? Method 3.
You understand? Why? I mean, this one
Method 3 is
this is the first method.
comparison.
Easy.
So for method 3, what I want you to know, so I'll bring up that color again. Remember we had that part that I was saying is x with theta less than 1. We say that this is an underdamped system.